Hello, so today I wanted to go over a little graph thing that I built. I'll be dropping a string for the blueprint for this. Um, it's kind of interesting. What it does is you feed it inputs and it's got a refresh rate built into it. That's this F value for frequency. And one of the interesting things about this graph is it will filter the incoming inputs and create a much more stable output along the x-axis here. So it's really easy to see. It's really easy to get an idea of what the incoming data is doing, even if that incoming data is very chaotic. I use this for timing trains in my intersection tests, which is probably something I'll go over in another video. But the graph itself is pretty cool, so I wanted to just talk about that, just in case anybody was as interested in this kind of stuff as I am. So in this demonstration, all I've hooked up is a little timer right here that counts to 20 and then resets and is continually doing that. And it's feeding its inputs into this graph. So this graph, you can see the leading edge right here is live, and the edges after that, or the columns after that, are progressively more and more filtered until the graph stabilizes. You can see the graph around this area is just basically translating. There's no more stabilization. But towards this side, you can see the inputs are coming in extremely noisily, and by about this point, they're pretty well filtered. They've pretty much been completely filtered. So yeah, so I'll go into a little bit about the way it works internally. So it's got a little clock, as I mentioned before, which is going to count up to a particular frequency. This frequency has to be greater than 3 for math reasons. It has to do with the way that it does the internal filtering. So you couldn't ever achieve like a fluid frame rate of like 1 frame per second, but you can get as good as one frame every 3 ticks, which is pretty smooth. I actually only use this with on frequencies of like 1 to 15 or even 1 to 60 ticks, 1 frame every 60 game ticks, just because the data coming in that I'm usually looking at is really broad. I'm usually looking for things in the minute time frame as opposed to the second to second time frame. So every time this graph refreshes, what it's going to do is it's going to display the current results on this first column. It's also going to output the average. Is going to be one of the lights is going to be the average, and that's calculated just by taking the number of rows and dividing by the value of each, or the number of columns and dividing by the current value in each column. And that's being done right here. U is the average. I also, just for the sake of, just to make things a little bit easier, I've got a little light right here which symbolizes 10, or it's at the 10 mark. So anything above this is going to be, a value of 10. And I usually, when I'm working with this thing, I'll usually try and make 10 nicely correlate with some other number. So going back to my intersection test, what I'll do is I'll make it so that I'll multiply the inputs by some magic number, so that if the inputs are, say, 1 train per second through this intersection, then that'll correspond to an incoming value into this graph of 10, and then we'll be able to see the fraction above or below 1 train per second coming through here in real time. So the way that the filtering works is cool for 2 reasons. The first reason is that it creates really stable outputs. So basically the outputs will always result in a line of connected dots at some point. It always converges to a line of connected dots. And that's really helpful for getting a good idea of what the values are doing, what the incoming values are doing in general, even if there's a lot of noise. Because you're never going to have neighboring cells scattered by more than two lights once the filtering is once you've reached probably about a third of the way through. You're probably going to see that the line is extremely coherent. The second cool thing about the filtering is you can just add additional rows on here. You could just build more, and there's no need to add in any additional programming. So I guess another way of saying that is this graph is perfectly tileable along the x direction. So you could, if you wanted to, you could make some pretty crazy like mile-long graphs. I've thought of doing that. Probably do that for another factory or another use case. But for this one, I got tired of building or got tired of requesting lights and plunking things down. And this is more than enough for my use case. So now I'd like to talk about the filtering. So the way that it works is every tick, every tick, and tick is specified by this. So a tick right here is 3 frames. So every 3 frames essentially, each column is going to look at the previous value of the column to the right of it. It's going to take that number and it's going to feed it into these combinators, and it's going to multiply by 2, add 1, and then divide by 2. And the reason why it does that is because the integer math that these combinators work off of results in rounding errors. They always round down if you're feeding in positive integers. So you have to add in 0.5 basically. And the only way that I know how to do that is to multiply by 2, add 1, and then divide by 2. You can't actually add a 0.5, so that's how I get around that. Concretely, the way that this works is each of these guys is, well, some of these combinators, so each of these 3 combinators corresponds to the row that it's built over top of, right? So all these combinators are going to be for this row, all these combinators are going to be for this row, right? So vertically, these guys correspond to the lights that are below them vertically. So so the way that this actually works concretely is maybe the easiest way to describe how this is working is to go backwards. So at the end, we've got a combinator that's doing 2 jobs. Its job is to work as memory, so it needs to store values. And its second job is it also needs to average the stored value with new incoming values as they're emitted. And so the way that I did that is I came up with kind of a cool trick, and what I do is I divide all the input signals by the input t. And the reason why that is super useful for this particular use case is because without any external input, if this guy's just left to do the same thing every frame, so if this graph was, or if the frequency was basically set to like infinite and the graph were to stop, what would happen is each combinator will be stuck in a cycle where it divides whatever's coming in by t, and then outputs that, and then feeds that back into itself, and then divides by t. But after you iterate once, t becomes 1 because t over t is 1, and the output value, whatever other input values there are, will stay the same. So in doing that, what I can do is use these guys as working memory, and every time I want to average in new values, I will pulse the value that I want to add in for a particular frame, as well as a value of t. And so the next step is, how do we come up with the input values, and how do we come up with t? Well, probably the best way to dig into that is I take a timer coming in, which is this guy right here, which is constantly counting up to, it's constantly incrementing a t value until it reaches the frequency, and then it will reset. So this clock is constantly cycling, 1, 2, and then 3, and then reset, 1, 2, 3, and reset, and that's because 3 is the frequency. What I'm going to do is I'm going to take that input clock signal, the clock is the t value, and I'm going to also input whatever incoming data is coming in the graph, which is v, and I'm going to multiply both of those guys by 2. And so this clock signal is constantly racing up, 0, 2, 4, 6, 8, yada yada, and then resetting 0, 2, 4, 6, 8. And the incoming values are also scaled by 2. Then what I'm going to do is I'm going to run all those into the next row of combinators. And in this row of combinators, I add a value of v, which is 1. So at this point, at this stage in the process, we've got 2 times v plus 1v, and we've also got 2 times t coming into this thing. And what I'm looking for is whenever t equals 2, I will output all of the inputs. So what's coming into here on signals where we are at t equals 2, what's coming into the bottom row is t is 2, v will be 2v plus 1, and what we're going to do is we're going to add all that to whatever's currently being stored in these guys and then divide by t. So it's a little, maybe that's a little weird to think about, a little bit kind of gross logic, but it keeps the number of combinators down if I do it that way, and it also results in this very coherent output. So yeah, so I hope you enjoy it. Happy to, if you've got any feedback you'd like to share. Yeah, have fun.